Tonight, we're going to do something no human has ever done. We're going to leave the solar system entirely, fly out beyond everything we know, turn around, and look back. And what we're going to see is going to shock you. Because the solar system you've been picturing your entire life, that neat circular diagram with the sun in the middle and the planets lined up in tidy orbits, that image is almost completely wrong. The real solar system looks nothing like that. From the outside, most of it is invisible. The planets essentially vanish. The distances between them are so absurdly vast that the entire structure becomes something you'd struggle to even notice against the background of interstellar space. What you'd actually see is stranger, emptier, and more haunting than any textbook has ever shown you. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Close your eyes for a moment and picture the solar system. I'm willing to bet I know exactly what you're imagining. A bright yellow sun sitting in the middle, Mercury close by, then Venus, then Earth with its little moon, Mars, maybe an asteroid belt, then the big ones, Jupiter, Saturn with its rings, Uranus, Neptune, all of them arranged in neat concentric circles, evenly spaced, colourful, and clearly visible. Maybe there's a black background with some stars sprinkled in. Maybe the planets are shown at slightly different sizes, with Jupiter being the biggest. The whole thing looks organised, compact, almost cozy. Like a family portrait where everyone is standing shoulder to shoulder, smiling at the camera. You've seen this image 1,000 times. It's on classroom walls, in textbooks, on websites, in documentaries, on posters in children's bedrooms. It's probably the single most reproduced scientific diagram in human history. And it is, in almost every way that matters, a lie. Not a malicious lie. Not an intentional deception designed to mislead you. It's a practical lie. A lie born out of necessity. Because the real solar system is so vast, so empty, and so absurdly disproportionate in its scales that if you drew it accurately, you wouldn't be able to see anything. The diagram would be useless. You'd have a dot for the sun and then inches or feet or miles of blank paper before you reach the next tiny dot. No publisher, no teacher, no documentary filmmaker can work with that. So they compress it. They shrink the distances. They inflate the planet sizes. They bring everything together so it fits on a page or a screen. And in doing so, they create an image that is convenient, understandable, and almost entirely misleading about what the solar system actually looks like. This matters. It matters because the compressed diagram doesn't just simplify reality. It fundamentally distorts your intuition about space. It makes you think the planets are relatively close together. It makes you think the solar system is a crowded, busy place, filled with large, visible objects. It makes you think that if you could somehow float above it all and look down, you'd see a beautiful arrangement of worlds orbiting the sun in a clearly defined structure. None of that is true. The real solar system is overwhelmingly empty. The planets are separated by distances so enormous that they defy easy comprehension. And from any meaningful distance outside the system, almost nothing would be visible at all. The sun would be a point of light. The planets would be gone. The whole thing would look like nothing. Let me show you what I mean. Let's try to build the solar system at its real scale and see what happens. The sun has a diameter of about 864,000 miles. It's enormous. You could fit roughly 1.3 million Earths inside it. It contains 99.86% of all the mass in the solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust, all of it together makes up just 0.14%. The Sun dominates the solar system so completely that everything else is almost a rounding error. Now, Earth orbits the Sun at an average distance of about 93 million miles. This distance is so important in astronomy that it has its own name, 1 astronomical unit, or AU. Light covers this distance in about 8 minutes and 20 seconds. If you could drive a car at highway speed, say 60 miles per hour, and somehow drive straight from Earth to the Sun without stopping, it would take you about 177 years. You would die of old age many times over before you arrived. And that's just the distance from Earth to the Sun. That's not even a large distance by solar system standards. That's the close neighborhood. Let's put this in a scale model. Imagine you shrink the Sun down to the size of a basketball. A standard basketball is about 9.4 inches in diameter. At this scale, how far away would Earth be? You might guess a few feet. Maybe across the room, maybe across a tennis court. The answer is about 86 feet. That's roughly the length of a large house. The Sun is a basketball sitting on your front porch, and Earth is a tiny grain of sand, smaller than a peppercorn, about 2 millimeters across, sitting 86 feet away at the far end of your yard. Already, the picture in your head is starting to break down. The neat diagram with everything close together doesn't work at real scale. The Sun and Earth are separated by a vast gulf of nothing, and Earth itself is so small relative to that distance that you'd struggle to see it. But let's keep going because it gets much worse. In this same model, where the Sun is a basketball, Mercury would be a grain of sand about 33 feet from the basketball. Venus would be another grain of sand about 62 feet away. Mars would be a slightly smaller grain of sand about 131 feet from the Sun. Already, we're covering the length of a large building, and we haven't even left the inner solar system yet. Every planet so far has been a tiny grain, barely visible, separated by tens of feet of empty space. Now we reach Jupiter. Jupiter is the largest planet in the solar system. Its diameter is about 86,881 miles, roughly 11 times wider than Earth. In our model, Jupiter would be about the size of a large marble, roughly an inch across. That's noticeably bigger than the grains representing the inner planets, but still small. And how far from the basketball Sun would this marble be? About 448 feet. That's almost a tenth of a mile. You'd need to walk nearly a city block and a half from the basketball before you reach Jupiter. And Jupiter is the closest of the giant planets. Saturn, with its spectacular rings, would be a slightly smaller marble, sitting about 823 feet from the Sun. That's more than 2.5 football fields away. Uranus would be a small bead about 1,656 feet out. That's nearly a third of a mile. And Neptune, the most distant planet, would be another small bead sitting about 2,593 feet from the Sun. That's almost exactly half a mile. So in our scale model, where the Sun is a basketball, Neptune is half a mile away. And Neptune itself is roughly the size of a small bead. Think about what that means for a moment. You're standing at one end of a half-mile stretch. At the far end is a basketball. Scattered along this half mile are a few grains of sand and a couple of small marbles and beads. That's it. That's the solar system. Everything else, Every single inch of that half mile that isn't occupied by one of these tiny objects is empty space. Nothing. Void. The overwhelming majority of the solar system is absolutely nothing at all. If you actually built this model and then tried to see the planets from the sun's position, you couldn't. They'd be too small and too far away. Even Jupiter, the largest planet, would be an unimpressive marble sitting 1/10 of a mile away. You wouldn't notice it. You certainly wouldn't see it without knowing exactly where to look. And Earth, your home, the world that contains everything you have ever known, every mountain, every ocean, every city, every person who has ever lived, would be an invisible speck less than 100 feet away. Invisible not because it's hidden, but because it's simply too small relative to the distance. This is the first great lie of the textbook diagram. The planets are not visible landmarks in the solar system. They're tiny, isolated objects separated by enormous voids of empty space. A diagram that shows them as colourful spheres neatly arranged around the sun gives you a completely false impression of their prominence. In reality, if you could somehow hover above the solar system and look down, the planets would not stand out. They would not catch your eye. They would not form an obvious pattern. They would be essentially invisible against the blackness unless you knew precisely where to look and had instruments powerful enough to detect them. And here's the part that really breaks people's intuition. Even the sizes of the planets relative to the distances between them are almost impossible to grasp. Consider the space between Earth and Mars. At their closest approach, when both planets are on the same side of the Sun and their orbits bring them nearest to each other, Earth and Mars are about 34 million miles apart. At their most distant, when they're on opposite sides of the Sun, they can be over 250 million miles apart. Even at their closest, 34 million miles is a staggering distance. The Perseverance rover, which landed on Mars in 2021, was launched when Mars was at a favourable position, and even then, the spacecraft took about 7 months to make the journey. The space between Jupiter and Saturn is even more extreme. Jupiter orbits at about 484 million miles from the Sun. Saturn orbits at about 890 million miles. The gap between them is roughly 406 million miles. That's more than 4 times the distance from Earth to the Sun. There is a vast empty ocean of space between these two planets where there is essentially nothing. No landmarks, no features, no signposts, just millions upon millions of miles of vacuum. This emptiness extends in every direction. The solar system is not a flat plane filled with stuff. It's a flat plane with almost nothing in it. The total volume of space enclosed by Neptune's orbit is staggering. If you drew a sphere around Neptune's orbit, it would have a radius of about 2.8 billion miles and a volume of roughly 92 billion cubic miles. Now, add up the volume of every planet, every moon, every asteroid, every comet, every piece of dust and debris in the solar system. All of it together occupies a tiny fraction of that volume. The solar system is more than 99.99999% empty space. The matter in it, all of it, including the sun itself, is like a few grains of sand scattered inside a cathedral. This is why the textbook diagram exists. Because if you try to draw the solar system at its true scale on a piece of paper, you get a blank page. The sun would be a microscopic dot. The planets would be far too small to represent. The distances between them would require a piece of paper miles long. No useful information could be conveyed, because at true scale, the solar system is visually empty. The only way to make it comprehensible is to cheat. to inflate the planets, compress the distances, and create an image that communicates the order and arrangement of the solar system, even though it completely misrepresents the actual appearance. And this compression doesn't just affect how we picture distances. It affects how we think about what the solar system looks like from the outside. Because the diagram trains our brains to think of the solar system as a thing, a coherent, visible structure with recognizable features. We imagine that if an alien spaceship were approaching our solar system from interstellar space, they'd see something. A disk of planets, a glowing arrangement, something that looks like the pictures, but they wouldn't. What they'd see, if they could see anything at all, is a star. Just a star. One point of light among billions in the galaxy. The planets orbiting that star would be completely undetectable to the naked eye at any significant distance. They're too small, too dim, and too close to the overwhelming glare of the sun. Think about how we detect planets around other stars. We can't see them directly in most cases. Exoplanets are detected through indirect methods. The transit method watches for tiny dips in a star's brightness when a planet passes in front of it. The radial velocity method measures tiny wobbles in a star's motion caused by a planet's gravity tugging on it. Direct imaging of exoplanets is extraordinarily difficult and has only been achieved for a handful of very large planets orbiting very far from their stars. This is because planets don't produce their own light in the visible spectrum. They only reflect the light of their star, and they reflect only a tiny fraction of it. Earth, for example, reflects about 30% of the sunlight that hits it. But Earth is so small and so close to the sun that from even a nearby star's distance, Earth's reflected light would be roughly 10 billion times fainter than the sun's direct light. Picking out Earth would be like trying to see a firefly hovering next to a lighthouse from 1,000 miles away. Jupiter does better because it's larger, but even Jupiter would be enormously difficult to see. From the distance of the nearest star, Proxima Centauri, about 4.24 light years away, Jupiter would be about 1 billion times fainter than the Sun. You'd need an extraordinarily powerful telescope with special instruments designed to block the star's glare just to have a chance of spotting it. And Jupiter is the best case scenario. It's the largest planet we have. The smaller planets, Mercury, Venus, Earth, Mars, would be hopelessly lost in the sun's brilliance. This tells us something fundamental about what the solar system looks like from the outside. It doesn't look like a system at all. It looks like a star. A single, solitary, ordinary star. There's no visible entourage of worlds, no obvious disk of orbiting bodies, no hint that 8 planets and hundreds of moons and millions of asteroids and billions of comets are orbiting that point of light. All of that complexity, all of that richness, all of the worlds we've spent decades exploring with spacecraft, it's all hidden, compressed into a single unresolvable point by the tyranny of distance and the feebleness of reflected light. This is perhaps the most important thing to understand before we go further. The solar system is not a visually impressive object. It's not a thing you can look at and say, there it is, I can see its shape. From the outside, from any distance greater than a few billion miles, it's just a star. Everything else is too small, too faint, and too spread out to register. The textbook diagram makes us feel like the solar system has a visual identity, a recognizable form. It doesn't. Its identity is the sun. The sun is the solar system as far as any external observer is concerned, unless that observer has very sophisticated instruments and knows exactly what to look for. Let me drive this home with one more comparison. You've probably seen images from NASA's Voyager missions. Voyager 1, launched in 1977, is now the most distant human-made object from Earth. As of 2025, it's about 15 billion miles from the Sun, roughly 163 times the distance from Earth to the Sun. In 1990, when Voyager 1 was about 3.7 billion miles from Earth, the spacecraft turned its camera back toward the inner solar system and took a series of photographs that were assembled into what's called the family portrait. One of those images captured Earth. In that photograph, Earth appears as a tiny pale blue dot, less than a pixel in size, a speck of light suspended in a ray of scattered sunlight. From just 3.7 billion miles away, which is still well within the solar system, Earth was barely detectable. It was almost lost in the noise of the camera's sensor and the glare of sunlight scattered through the camera's optics. If the camera hadn't been pointed at exactly the right spot, Earth wouldn't have been seen at all. And Voyager 1 was still inside the solar system when it took that photo. It hadn't even reached the heliopause yet, the boundary where the sun's influence gives way to interstellar space. From that relatively modest distance, Earth was already a barely visible speck. Now imagine looking back from the distance of Proxima Centauri, 4.24 light-years away, about 25 trillion miles. At that distance, not only would Earth be invisible, but even the sun would be reduced to just another star in the sky. A bright one, certainly, but just a point of light. Nothing about it would tell you that 8 worlds and a whole complex system of objects orbit around it. The astronomer Carl Sagan reflected on Voyager's pale blue dot image with words that have become some of the most quoted in the history of science. He spoke about how that tiny point of light contains everything we've ever known. Every human who has ever lived, loved, suffered, and triumphed did so on that barely visible mote of dust. And he was speaking about a view from within the solar system. From outside it, even that pale blue dot would disappear entirely. So this is where we start. Not with the neat diagram, not with the colourful planets arranged in tidy orbits, but with the truth. The solar system, seen from outside, is almost entirely invisible. It's a star surrounded by unimaginable emptiness, with tiny, faint, widely scattered objects that no unaided eye could detect from any meaningful distance. The diagram in your textbook didn't just simplify reality, it inverted it. It made the solar system look full when it's actually empty. It made it look compact when it's actually vast. It made it look visible when it's actually hidden. Everything you thought you knew about what the solar system looks like is based on a picture that was designed to be useful, not accurate. And that means everything you're about to learn is going to require you to let go of that picture, to abandon the neat, colourful, crowded diagram and replace it with something far stranger. A system so vast and so empty that the objects in it are like isolated atoms in an enormous void. A system where the distances between worlds are not gaps between neighbours, but chasms between civilizations. A system where the only thing visible from the outside is a single star, burning alone in the darkness, giving no hint of the extraordinary complexity hidden in its gravitational embrace. Because the truth is, the solar system's real appearance is not about what's in it. It's about what's between what's in it. The defining feature of our solar system is not its planets or its sun. It's the space, the emptiness, the void. That's what dominates. That's what defines the structure, and that's what makes the real solar system so radically different from the picture in your head. What we're going to discover as we continue this journey is that the solar system has layers of structure that the textbook diagram never shows. There are regions beyond the familiar planets that extend the system's boundaries far, far beyond what most people imagine. There are sparse clouds of icy objects scattered across billions of miles. There's a bubble of solar wind pressing against the gas between the stars, defining a boundary that gives the solar system its true outer shape. And none of it, not a single part of it, looks anything like what you've been taught to picture. The real solar system is vast, dark, sparse, and almost entirely empty. And understanding that emptiness, understanding why the planets vanish and the distances crush everything into invisibility, is the first step toward understanding what this system would actually look like if you could somehow step outside of it and look back. So now let's actually do it. Let's leave. Let's fly out past the planets, past everything familiar, and position ourselves at various distances from the sun. And let's ask the simplest possible question. What do we see when we look back? Let's start relatively close. Let's place ourselves just beyond the orbit of Neptune, about 30 astronomical units from the sun. That's roughly 2.8 billion miles. In cosmic terms, this is still very much inside the solar system. We haven't left. We're still well within the gravitational dominion of the sun, still inside the region where planets orbit. But even from here, things already look radically different from anything the textbook prepared you for. The first thing you'd notice is the sun. From Neptune's distance, the sun is still the brightest object in the sky by an enormous margin. But it doesn't look like the sun you know from Earth. From Earth, the sun appears as a large, blazing disk that you can't look at directly without damaging your eyes. It spans about half a degree of sky, roughly the width of your pinky finger held at arm's length. From Neptune's distance, that disk has shrunk. The sun is now about 900 times smaller in area than it appears from Earth. It would appear as an intensely bright point, still far brighter than any star in the night sky, but noticeably smaller. You could almost mistake it for an extraordinarily brilliant star, rather than the massive furnace it actually is. It would still cast light. It would still illuminate anything nearby. But the warmth would be gone. At Neptune's distance, the sunlight is about 900 times weaker than at Earth. The temperature out here hovers around minus 330 degrees Fahrenheit. This is a cold, dim frontier. The sun's colour would be subtly different too. Not dramatically, but noticeably if you were paying attention. From Earth, we see the sun as a warm, yellowish white, partly because of how our atmosphere scatters its shorter wavelengths. From 30 astronomical units, with no atmosphere between you and the sun, you'd see its true colour more clearly. A clean white point with just a hint of warmth to it. The unfiltered output of a G-type main sequence star with a surface temperature of about 10,000 degrees Fahrenheit. It would look sharper, more precise, less like the golden, familiar sun of a summer afternoon, which gets its rich yellow tone from Earth's atmosphere scattering away shorter wavelengths, and more like what it actually is. A distant thermonuclear furnace radiating across the electromagnetic spectrum. You'd start to see the sun the way astronomers see other stars, as an object with a spectral classification and a colour temperature, rather than the golden presence that dominates your sky on Earth. This subtle shift in perception, From the sun as a life-giving companion to the sun as just another point of stellar light is one of the first psychological shocks of leaving the inner solar system. Now, from this position beyond Neptune, look back toward the inner solar system. Where are the planets? Can you see them? The answer is deeply humbling. The inner rocky planets, Mercury, Venus, Earth, and Mars, are all clustered so close to the sun that from Neptune's distance, they would be buried in the sun's glare. Think about what this means. Mercury orbits at about 0.39 astronomical units from the sun, Venus at 0.72, Earth at 1 AU, Mars at 1.52. From 30 AU away, all four of these planets are compressed into a tiny angular region right next to the sun. The maximum angular separation between Earth and the sun as seen from Neptune is only about 1.9 degrees. That sounds like a measurable amount, but remember, you're trying to spot a tiny dot of reflected light right next to an intensely bright source. It would be like trying to see a grain of dust floating an inch away from a flashlight beam aimed at your eyes from across a football field. The flashlight overwhelms everything near it. Even under the most favorable conditions, with the planets at maximum elongation from the sun as seen from your position, the inner planets would be extraordinarily faint. Earth, the brightest of the terrestrial planets as seen from this distance, would shine at roughly the brightness of a moderately dim star, but it would be sitting right next to something enormously brighter. The contrast would make it nearly impossible to pick out without specialized instruments. Mercury and Mars would be even fainter. For all practical purposes, the inner solar system from Neptune's distance is invisible. It's consumed by the sun. The four rocky worlds where humanity lives and has sent its rovers and probes would simply vanish into the solar glare as if they never existed. This is not an exaggeration. When the Voyager spacecraft were out near Neptune's orbit and looked back toward the sun, the inner planets were extraordinarily difficult to detect. The pale blue dot image of Earth that Voyager 1 captured required precise pointing, careful exposure timing, and even then, Earth was less than a single pixel. From Neptune's distance, the entire inner solar system collapses into the immediate neighborhood of the sun and becomes functionally invisible to any observer looking with unaided eyes. What about the outer planets? Surely from just beyond Neptune you could see Jupiter and Saturn. They're enormous planets. Jupiter alone is 11 times wider than Earth. Its cloud tops reflect a substantial amount of sunlight. Saturn's rings make it one of the most reflective objects in the outer solar system. Can you see them from here? The answer is yes, but barely. And not in the way you might imagine. Jupiter, from a position 30 astronomical units away, would be roughly 25 astronomical units distant when it's on the same side of the sun as you. At that distance, Jupiter would appear as a bright point of light, not a disk, not a sphere with visible cloud bands and a great red spot, just a point, a dot. Brighter than most stars in the background sky, certainly, but still just a dot. You would have no way of knowing from looking at it that it's a massive gas giant with a diameter of nearly 87,000 miles, that it has at least 95 moons, that it contains more mass than all the other planets combined. All of that information is compressed into a single, dimensionless point of reflected sunlight. And speaking of those moons, they're gone too. Jupiter's moon system is one of the most remarkable collections of worlds in the solar system. The four Galilean moons, Io, Europa, Ganymede, and Callisto, are worlds in their own right. Ganymede is larger than the planet Mercury. Europa almost certainly has a liquid water ocean beneath its icy surface, an ocean that might harbour life. Io is the most volcanically active body in the solar system, its surface constantly being reshaped by eruptions powered by the gravitational tug-of-war between Jupiter and the other large moons. These are fascinating, complex worlds that we've spent decades studying with spacecraft. And from just beyond Neptune, every single one of them is completely invisible. They're far too small and far too faint to detect. They orbit so close to Jupiter that even if you could somehow see Jupiter as a disk, which you can't, the moons would be lost in its glare the same way the inner planets are lost in the sun's glare. The entire Jovian system, a miniature solar system in its own right with dozens of moons and a complex web of gravitational interactions, collapses into a single featureless dot. The same is true of Saturn's moons. Titan, larger than Mercury with a thick atmosphere and lakes of liquid methane on its surface, invisible. Enceladus, with its geysers of water shooting into space from a subsurface ocean, invisible. The dozens of smaller moons shepherding Saturn's rings and creating complex gravitational resonances, all invisible. Every moon system in the solar system, every one of those intricate miniature worlds, vanishes completely from this distance. They don't contribute enough reflected light to register against the blackness. They're there, orbiting faithfully, but you'd never know it. Saturn would be visible too, a fainter point of light. Its rings, those magnificent structures that make it perhaps the most visually iconic object in the solar system, would be completely invisible. The rings are wide but extremely thin, and from tens of astronomical units away, they contribute some brightness to Saturn's overall appearance, but add no visible structure. Saturn would be a dot, dimmer than Jupiter, indistinguishable from a star to your naked eye, except for the fact that over weeks and months, you might notice it moves against the background of fixed stars. Uranus, closer to your position, would actually be relatively nearby in this scenario, perhaps just a few astronomical units away, depending on orbital positions. But Uranus is small, only about 4 times Earth's diameter, and it reflects light poorly. It would appear as a faint point, visible but unremarkable. Neptune itself, if you're just beyond its orbit and looking back, would also be a dim point of reflected sunlight behind you. So here's the picture from just beyond Neptune. You see the sun, still bright, but diminished. Near it, lost in its glare, the 4 inner planets are invisible. Scattered across the sky at various positions are a few faint points of light representing the giant planets. Jupiter is the brightest. Saturn is dimmer. Uranus and Neptune are dimmer still. None of them show any detail. None of them look like planets. They look like stars. If you didn't already know they were there, if you didn't have a map of their positions, you might not notice them at all amongst the thousands of background stars. And here's something that makes this even more disorienting. The planets are not clustered together in one part of the sky. They're scattered. Each planet orbits the sun at a different speed and at a different distance. At any given moment, they could be anywhere along their respective orbits. Jupiter might be on one side of the sun from your perspective, Saturn on the other side, Uranus somewhere else entirely. There's no neat arrangement, no orderly procession, just a few faint dots sprinkled across different parts of the sky, each one tracing its own slow, independent path around a bright central point. This is a crucial difference from the textbook image. In the diagram, the planets appear to form a coherent structure. They're shown in a line or arranged in concentric circles, and your eye naturally groups them together into a single visual system. In reality, at any given moment, the planets are spread out around the sun at various angles. They don't form a visible pattern. They don't create a recognizable shape. The solar system has no visible structure from the outside. It's just a scattering of isolated dots that happen to be gravitationally bound to the same star, but show no visual evidence of that relationship. Now let's talk about something most people never think about: the orbital planes. In the textbook diagram, all the planets orbit in a perfectly flat plane. They're shown as circles or ellipses, all lying in the same sheet, like grooves on a vinyl record. This is approximately true, but only approximately. In reality, each planet's orbit is tilted slightly relative to the others. The reference plane for the solar system is called the ecliptic, which is essentially the plane of Earth's orbit around the Sun. Most of the other planets orbit close to this plane, but not exactly in it. Mercury's orbit is tilted about 7 degrees relative to the ecliptic. That might not sound like much, but at the distances we're talking about, it matters. 7 degrees of tilt means that Mercury can be significantly above or below the plane where you'd expect it based on the textbook diagram. Venus is tilted about 3.4 degrees, Mars about 1.85 degrees, Jupiter is tilted only 1.3 degrees, Saturn about 2.5 degrees, Uranus about 0.8 degrees, Neptune about 1.8 degrees. These tilts mean that the planets don't all orbit in exactly the same flat sheet. There's a slight thickness to the system. If you could somehow see all the orbits at once, they wouldn't form a razor-thin disk. They'd form something more like a slightly puffy pancake, with orbits crossing above and below each other at small angles. Mercury, with its relatively large tilt, wanders the farthest from the average plane. The gas giants stay closer to the ecliptic, but still deviate slightly. From the outside, this means that if you viewed the solar system edge-on, looking along the plane of the ecliptic, you wouldn't see all the planets lined up in a perfect flat line. Some would be slightly above the plane, some slightly below, depending on where they are in their orbits. The system would have a slight vertical spread. Not much, but enough that it wouldn't appear as the perfectly thin disk the diagrams imply. From above the ecliptic, looking down on the system, the slight orbital tilts wouldn't be noticeable because you'd be looking at the orbits face-on. The planets would appear to move in nearly circular paths in roughly the same plane. But you still wouldn't see much because, as we've established, the planets themselves are tiny points of light separated by enormous distances. The orbital tilts matter more than you might think because they tell us something important about the solar system's history. The fact that all the planets orbit roughly in the same plane is a direct consequence of how the solar system formed. About 4.6 billion years ago, a vast cloud of gas and dust began to collapse under its own gravity. As it collapsed, it spun faster, the same way a figure skater spins faster when they pull their arms in. That spinning caused the cloud to flatten into a disk. The sun formed at the center of the disk. The planets formed within the disk. And because they all formed from the same rotating disk, they all ended up orbiting in roughly the same plane. The slight tilts we see today are probably the result of gravitational interactions over billions of years. Planets tugging on each other, close encounters with passing objects. the slow accumulation of tiny perturbations over cosmic time. These interactions nudge the orbit slightly out of perfect alignment, but the overall flatness of the system, the fact that all the major planets orbit within a few degrees of the same plane, is a fossil record of that original spinning disk of gas and dust. This is relevant to what the solar system looks like from the outside because it means the system does have a preferred orientation. There is a plane. The planets do orbit approximately in a flat structure. If you're looking at the solar system from outside, and you happen to be viewing it close to edge on, looking along the ecliptic plane, you'd see the planets moving back and forth along a line. They'd appear to oscillate from one side of the sun to the other, like beads sliding along a wire. Of course, you still probably couldn't see them because they'd be too faint, but geometrically, that's what would be happening. If you were viewing from above or below the ecliptic, looking down on the system from the north or south pole, you'd see the planets tracing their nearly circular orbits around the sun. Again, the planets themselves would be invisible points, but the geometry of their motion would be roughly circular. The viewing angle matters because it affects what structures you might detect. From edge on, any disk-like feature of the solar system, like the asteroid belt or the Kuiper Belt, would appear as a thin line. From above, it would appear as a ring. We'll come back to this later when we discuss the outer structures, but the key point is that the solar system's appearance depends significantly on your viewing angle. This is something the textbook diagram never communicates, because it always shows you the same overhead view with the orbit spread out nicely. Now let's address one of the most persistent misconceptions about the solar system: the asteroid belt. In movies and television, the asteroid belt is shown as a dense, dangerous field of tumbling rocks. Spaceships weave and dodge between boulders that threaten to smash into them at every turn. In Star Wars, Han Solo famously pilots the Millennium Falcon through an asteroid field where rocks are mere feet apart, crashing into each other, creating a chaotic obstacle course. The real asteroid belt is nothing like this, not even remotely close. The asteroid belt sits between the orbits of Mars and Jupiter, roughly 2 to 3.5 astronomical units from the Sun. It contains millions of asteroids, which sounds like a lot, but the volume of space the belt occupies is absolutely enormous. The belt is a ring with an inner radius of about 2 astronomical units and an outer radius of about 3.3 astronomical units, and it has some vertical thickness above and below the ecliptic plane. When you calculate the total volume of this region, it's staggeringly large, and the asteroids within it are small. The largest asteroid, Ceres, is only about 580 miles across. That's smaller than the state of Texas. Ceres is so small that you could fit about 13 of them side by side across Earth's diameter, and Ceres is by far the largest object in the belt. The next largest, Vesta, is about 326 miles across. Most asteroids are far smaller, just a few miles or even a few hundred feet across. Many are the size of houses or cars. When you add up the total mass of everything in the asteroid belt, all the millions of asteroids combined, the total comes to less than 4% of the moon's mass. The entire asteroid belt contains less mass than a small moon. If you gathered every asteroid in the belt and combined them into a single object, that object would be smaller than Earth's moon, significantly smaller. The average distance between asteroids in the belt is enormous. Estimates suggest the average spacing is somewhere around 600,000 miles to 1 million miles between objects larger than a kilometer. That's roughly 2 to 4 times the distance from Earth to the moon. You could fly through the asteroid belt in a straight line and have virtually zero chance of encountering an asteroid. In fact, multiple spacecraft have done exactly this. Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, Galileo, Cassini, New Horizons, and others have all passed through the asteroid belt on their way to the outer solar system. None of them hit anything. None of them even came close to hitting anything. Mission planners didn't need to calculate evasive maneuvers. They just flew straight through because the belt is almost entirely empty space. From outside the solar system, the asteroid belt would be completely invisible. The individual asteroids are far too small and far too faint to detect. They don't reflect enough sunlight to be seen at interstellar distances. Even from within the solar system, you can't see the asteroid belt as a structure. You can see individual asteroids if you know where to point a telescope, but the belt as a whole has no visible presence. There's no ring of light, no band of rocky material, no discernible structure. It's a vast region of space that happens to contain some small rocks scattered absurdly far apart. This is important because many people imagine the asteroid belt as a visible feature of the solar system, something that would be obvious. From the outside, a ring around the sun between Mars and Jupiter. It's not. It's another ghost. Another invisible structure that exists in theory and in careful telescopic surveys, but has no visual presence whatsoever. The same is true of the dust in the inner solar system. There is a faint disk of dust called the zodiacal dust cloud, created by asteroid collisions and comet debris. From Earth, this dust is occasionally visible as a faint glow in the sky after sunset or before sunrise, called the zodiacal light. But this dust is incredibly thin and sparse. From outside the solar system, it would be undetectable. It doesn't form a visible disk. It doesn't create a glowing structure around the sun. It's there, but it's so diffuse that it might as well not be. Let me now push us farther out and see how the picture changes. Let's move to about 100 astronomical units from the sun. That's roughly 3 times Neptune's orbital distance, about 9.3 billion miles. At this distance, we've passed beyond the orbits of all the recognized planets. We're in the region where the solar wind is starting to slow down as it collides with the interstellar medium, but we haven't yet reached the heliopause. We're in a transitional zone. Voyager 1 passed through this region decades ago on its way out of the solar system. And what its instruments recorded as it crossed through this distance was extraordinary. Not because of what they detected, but because of how the environment was changing. Around this distance, Voyager's plasma instruments registered the solar wind beginning to falter. The stream of charged particles from the sun, which had been a constant presence throughout the spacecraft's journey, was thinning and slowing. The density of solar wind particles was dropping as they spread across an ever larger volume of space. At the same time, Voyager began detecting something else. A faint but rising hum of particles from outside the solar system, cosmic rays and interstellar ions pressing inward from the galaxy beyond. At 100 astronomical units, you're in a borderland. The sun's influence is waning. The galaxy's influence is growing. You're approaching the edge of the sun's domain, and you can feel it in the particle counts even though you can't see it with your eyes. From here, the sun is still the brightest object in your sky, but it's dimmed considerably. It's now about 10,000 times fainter than it appears from Earth. Still much brighter than any star, but noticeably less overwhelming. It would look like an exceptionally brilliant star, something that commands your attention but no longer dominates the entire sky. Its colour would be more apparent now. A warm, yellowish-white point, similar to how we see Alpha Centauri A from Earth's night sky. You'd be looking at the sun the way observers on other star systems see their own parent stars from great distances. A point of light with a specific colour and brightness, carrying information about its temperature and size in its spectrum, but revealing nothing about the family of worlds hidden in its glare. The planets are effectively invisible without instruments. Jupiter at its brightest would be an extremely faint point of light near the Sun. Saturn would be fainter still. The inner planets are hopelessly lost. The asteroid belt is non-existent as a visible feature. You are surrounded by darkness in nearly every direction. The only notable light source is the Sun, now reduced to a brilliant but small point behind you, and the stars, which look essentially the same from here as they do from Earth, because they're so incredibly far away that moving a few billion miles makes no difference to their apparent positions. This raises a fascinating point. The constellations you see from 100 astronomical units look identical to the constellations you see from Earth. Orion still looks like Orion. The Big Dipper still looks like the Big Dipper. The stars are so distant that shifting your position by the entire width of the solar system barely changes their apparent arrangement. You'd need to travel light years before the constellations would start to distort noticeably. From 100 astronomical units, the night sky is virtually unchanged. The only difference is that the Sun is no longer the blazing overhead presence it was on Earth. It's now just the brightest star in the sky, and everything else, the familiar constellations, the Milky Way band, the scattered points of distant suns, all of it looks exactly the same. This is a profound and somewhat eerie realization. You could travel billions of miles from Earth, far beyond every planet in the solar system, and look up at the night sky and see the exact same stars in the exact same positions. The universe is so vast that the entire solar system is a negligible point within it. Moving around inside the solar system changes nothing about the larger cosmos. It's like walking across a single tile on a floor that stretches for miles. Your movement is real, but it's imperceptible against the scale of everything else. Now let's pull back even further. Let's go to 1,000 astronomical units. That's about 93 billion miles from the Sun, roughly 10 times farther than our last stop. At this distance, we're well beyond the heliopause. We've left the region of space dominated by the solar wind. We're in interstellar space, though still within the gravitational reach of the Sun. Objects out here take hundreds of thousands of years to complete a single orbit. From 1,000 astronomical units, the Sun is now roughly 100 times fainter than it was at 100 astronomical units. It's still bright. It would still stand out as one of the brightest stars in your sky, but it would no longer dominate. It would be one bright star among many, remarkable but not overwhelming. You might pick it out as being slightly brighter or slightly different in colour from its neighbours, but if you didn't know which star was the Sun, you might not find it immediately. It would take careful observation to distinguish it from the background. Its warm yellowish hue would still be faintly detectable, but it would look less like a sun and more like any number of similar G-type stars scattered across the sky. If you were an alien astronomer cataloguing stars, you might note it as an unremarkable main sequence star of moderate luminosity. Not particularly interesting, not worth a closer look. You'd have no reason to suspect it was anything special. And the planets? Completely gone. Absolutely invisible. Even Jupiter, the king of the planets, would be so faint at this distance that detecting it would require telescopes far more powerful than anything you could carry with you. The inner planets would be billions of times fainter than the Sun itself, utterly undetectable by any reasonable instrument at this range. The solar system's retinue of worlds has vanished entirely. All that remains is the star. Let me step back for a moment and summarize what we've discovered so far, because it's worth letting the weight of this settle in. We've positioned ourselves at 3 different distances from the Sun. From just beyond Neptune, about 30 astronomical units, the inner planets are lost in the Sun's glare and the outer planets are faint points of light scattered across the sky. Every moon system, from Jupiter's volcanic Io to Saturn's hydrocarbon-drenched Titan, has vanished entirely. From 100 astronomical units, the planets are essentially invisible. The solar wind is faltering around us, and the Sun has dimmed to a brilliant but small point that's beginning to resemble just another star. From 1,000 astronomical units, the Sun is just one bright star among many, and absolutely nothing else in the solar system can be detected. At every distance, the overwhelming impression is the same: emptiness. The solar system is not a bustling, crowded place. It's a single star accompanied by a handful of tiny, faint objects that disappear almost immediately as you move away from them. The rich, complex, fascinating system we've spent decades exploring with spacecraft, the system that contains worlds with volcanoes and oceans and ring systems and storms larger than Earth, all of it compresses into a single point of light as soon as you gain any meaningful distance. This is the reality that the textbook diagram hides from you. The diagram shows a solar system that looks like something. The real solar system from the outside looks like almost nothing. A star. Just a star. One among hundreds of billions in the Milky Way. There is no way to look at the Sun from outside and know that it hosts 8 planets, hundreds of moons, and at least one world teeming with life. All of that complexity, all of that wonder is hidden behind the punishing mathematics of distance and the limitations of reflected light. But here is what makes this story interesting. The planets are not the whole story. The familiar worlds between Mercury and Neptune occupy only a tiny fraction of the solar system's total volume. Beyond the planets, extending outward for billions of miles, there are other structures. Structures that are even more sparse and even more invisible than the planets, but that define the true size and shape of the solar system in ways most people never consider. Because when we talk about the solar system from the outside, we can't just talk about the planets. We have to talk about what lies beyond them. And what lies beyond them is going to redefine your understanding of how large this system really is and what shape it actually takes. The planets, as it turns out, are just the compact, innermost core of something much, much bigger. The solar system doesn't end at Neptune. It barely begins there. And the structures that extend beyond Neptune, the Kuiper Belt, the scattered disk, and the vast spherical cloud of icy bodies that envelops everything. These are the features that give the solar system its true outer form. They're also the features that no textbook diagram ever shows you properly because they're too large, too sparse, and too strange to fit into the neat picture you've been carrying in your head. The planets are the solar system's heart. But the body extends far beyond what any diagram has ever shown you. And understanding that body, understanding its real shape and extent, is the key to understanding what our solar system would truly look like if you could step outside it, turn around, and take in the whole thing at once. Most people think the solar system ends at Neptune, that beyond the last planet there's nothing but empty interstellar space stretching away to the nearest star. This is one of the biggest misconceptions in all of astronomy. The truth is that Neptune's orbit marks not the edge of the solar system, but something closer to its front porch. Beyond Neptune, extending outward for billions and ultimately trillions of miles, there are vast regions filled with objects that most people have never heard of. These regions are sparse, they are dark, they are cold beyond imagining, and they are enormous. So enormous that the entire zone containing the planets, everything from Mercury to Neptune, is just a small bright core at the center of a structure that dwarfs it in every dimension. To understand this, we need to visit these outer regions one at a time. And as we do, you're going to realize that the solar system is not the compact, well-defined thing the textbook taught you. It's something far larger, far stranger, and far emptier than you ever imagined. Let's start with the Kuiper Belt. This is the region immediately beyond Neptune, and it's the first of the solar system's outer frontiers. The Kuiper Belt extends from roughly 30 astronomical units near Neptune's orbit out to about 50 astronomical units from the Sun. That's a band of space stretching from about 2.8 billion miles to about 4.6 billion miles from the Sun. The belt is named after Dutch-American astronomer Gerard Kuiper, who in 1951 predicted that a band of icy objects should exist beyond Neptune, leftovers from the solar system's formation that never coalesced into a full-sized planet. Kuiper was right. Starting in 1992, astronomers began discovering objects in this region. The first confirmed Kuiper Belt object beyond Pluto was found by astronomers David Jewitt and Jane Liu using the University of Hawaii's telescope on Mauna Kea. The object, designated 1992 QB1, was small, faint, and incredibly distant. But it proved that the space beyond Neptune was not empty. Since then, over 2,000 Kuiper Belt objects have been catalogued, and astronomers estimate that the region contains hundreds of thousands of objects larger than 60 miles across and possibly trillions of smaller bodies. Pluto lives here. The world that was considered the ninth planet from its discovery in 1930 until its reclassification in 2006 is a Kuiper Belt object. It orbits the Sun at an average distance of about 39.5 AU, with an orbit that's noticeably more elliptical and more tilted than the major planets. Pluto's orbit is inclined about 17 degrees to the ecliptic plane, which means it wanders far above and below the flat disk where the 8 major planets travel. At times during its 248 Earth-year orbit, Pluto actually comes closer to the Sun than Neptune does, though their orbits are arranged so they never actually collide. Pluto is the most famous Kuiper Belt object, but it's not alone. There are other large bodies out here. Eris, discovered in 2005, is roughly the same size as Pluto, and actually slightly more massive. Its discovery was one of the key events that led to Pluto's reclassification. Because if Pluto was a planet, then Eris should be too. And astronomers realized they'd end up with dozens of planets, as more similar objects were found. Makemake and Haumea are 2 other large Kuiper Belt objects classified as dwarf planets. Haumea is particularly unusual because it rotates so fast, completing a full rotation in less than 4 hours, that it's been stretched into an elongated, egg-like shape. These are substantial objects, hundreds of miles across, with their own moons and their own complex histories. But they are tiny compared to the major planets and unimaginably far apart. And that's the critical point about the Kuiper Belt. It's not a belt in any visual sense. The word belt conjures an image of a dense band of material encircling the sun. Something thick and substantial that you could see. The reality could not be more different. The Kuiper Belt is a vast, sparse scattering of small icy objects spread across an enormous volume of space. The distances between individual Kuiper Belt objects are typically millions of miles. Most of these objects are small, dark, and incredibly faint. They reflect very little sunlight because they're so far from the sun that the sunlight reaching them is already feeble, and their surfaces are often coated with dark, radiation-processed organic compounds called tholins that absorb light rather than reflecting it. If you were floating in the middle of the Kuiper Belt and looked around, you would see nothing. Absolutely nothing that you could attribute to the belt. The nearest Kuiper Belt object might be millions of miles away, far too small and far too faint to see with the naked eye. You would see the sun, much diminished. You would see the stars, and that's it. The Kuiper Belt would be completely invisible to you despite the fact that you were inside it. There would be no sense of being in a belt or a ring or any kind of structure. Just the same cold, dark emptiness that fills the rest of space. From outside the solar system, the Kuiper Belt would be equally invisible. The individual objects are too small, too dark, and too widely spaced to create any detectable collective signal. Even the largest Kuiper Belt objects like Pluto and Eris are tiny by cosmic standards. Pluto is only about 1,473 miles across. From even a few light years away, Pluto would be so faint that the most powerful telescopes humanity has ever built couldn't detect it. The Kuiper Belt, as a structure, as a ring or a disk, has no visual presence. It exists only in our catalogues and our mathematical models. It has no silhouette, no glow, no outline. There's an important structural detail about the Kuiper Belt that the textbook diagrams, when they bother to show it at all, always get wrong. The Kuiper Belt is not a perfectly flat ring lying precisely in the ecliptic plane. It has significant vertical extent. Many Kuiper Belt objects have orbits that are substantially tilted relative to the ecliptic. Pluto's 17-degree inclination is one example, but there are objects with even more extreme tilts. Some Kuiper Belt objects travel on orbits inclined 30, 40, or even more degrees from the ecliptic plane. This means the Kuiper Belt is not a thin disk. It's more like a thick, puffy torus, a donut-shaped region with substantial vertical spread. This matters for understanding what the solar system looks like from the outside, because it means that even if you could somehow detect the Kuiper Belt, it wouldn't appear as a razor-thin ring. It would appear as a broad, diffuse zone surrounding the sun, thicker than the planetary disk, and less well-defined. The transition from the relatively flat inner solar system where the planets orbit to the puffier Kuiper Belt is one of the first hints that the solar system's structure becomes less organized and less planar as you move outward. Things get messier. The neat, flat, orderly picture of the inner solar system gives way to something more chaotic and more three-dimensional. Beyond the classical Kuiper Belt, things get even more interesting. There's a population of objects called scattered disk objects that orbit in a region overlapping with and extending well beyond the Kuiper Belt. These are icy bodies that were gravitationally scattered by Neptune's influence during the early solar system. Neptune, as it migrated outward in the first few 100 million years after the solar system formed, flung countless icy objects into highly elliptical, highly inclined orbits. These scattered disk objects have orbits that are far more extreme than typical Kuiper Belt objects. Their closest approaches to the Sun might bring them within 30 or 40 astronomical units, similar to the Kuiper Belt, but their farthest points can take them out to hundreds of astronomical units. Some scattered disk objects travel on orbits that carry them more than 1,000 astronomical units from the Sun before swinging back in. Eris, despite being classified with the Kuiper Belt objects, actually has characteristics of a scattered disk object. Its orbit takes it from about 38 astronomical units at its closest to about 97 astronomical units at its farthest. That's a huge elliptical path, carrying Eris from Neptune's neighborhood out to more than 3 times Neptune's distance before bringing it back. These scattered disk objects are important for understanding the solar system's shape, because their extreme orbits mean they occupy a much larger volume of space than the classical Kuiper Belt. While the Kuiper Belt is mostly confined to a thick torus between about 30 and 50 astronomical units, scattered disk objects range out to hundreds of astronomical units in all directions. Their high orbital inclinations mean they can travel far above and below the ecliptic plane. The scattered disk is less like a belt and more like a diffuse cloud, albeit one that's concentrated toward the ecliptic and denser closer to the Sun. If you could somehow map every scattered disk object and display them all at once, you'd see a swarm of elongated orbits spraying outward from the Sun in many different directions and at many different angles. It would look chaotic, disorganized, nothing like the neat concentric circles of the planetary orbits. The scattered disk is the solar system starting to lose its structure, starting to transition from the ordered flatness of the inner regions to something more spherical and more diffuse. And yet, even the scattered disk is not the edge, not even close, because beyond the Kuiper Belt, beyond the scattered disk, far out in the cold darkness where the Sun is just another star in the sky, there exists something so vast, so enormous, that it makes everything else in the solar system look compact by comparison. The Oort Cloud. The Oort Cloud is named after Dutch astronomer Jan Oort, who in 1950 proposed its existence to explain a puzzling observation about comets. Astronomers had noticed that some comets, called long-period comets, arrive in the inner solar system on orbits that take thousands or even millions of years to complete. These comets come from every direction. They don't arrive preferentially from the ecliptic plane like most solar system objects. They come from above, below, and every angle in between. Their orbits are randomly oriented, as if they're falling in from a spherical shell surrounding the Sun. Oort reasoned that there must be a vast reservoir of icy bodies surrounding the solar system at enormous distances. Gravitational perturbations from passing stars, from giant molecular clouds in the galaxy, and from the tidal forces of the Milky Way itself occasionally nudge these distant objects, changing their orbits just enough to send them falling inward toward the Sun. When one of these objects approaches the Sun, the solar heat vaporizes its ices, creating the spectacular tails that make comets visible. The Oort Cloud has never been directly observed. No telescope has ever imaged an Oort Cloud object in its native environment. Everything we know about it comes from inference, from studying the comets that fall inward from it and working backward to determine where they came from. But the evidence is strong. The existence of long-period comets with randomly oriented orbits essentially requires a spherical reservoir of icy bodies at extreme distances from the Sun. The numbers involved are almost impossible to process. The Oort Cloud is believed to begin at roughly 2,000 to 5,000 astronomical units from the Sun and extend outward to somewhere between 50,000 and 100,000 astronomical units. Let me put that in perspective. Neptune, the outermost planet, orbits at 30 astronomical units. The Kuiper Belt extends to about 50 astronomical units. The Oort Cloud begins at roughly 2,000 astronomical units, which is already 40 times farther out than the Kuiper Belt, and it extends to perhaps 100,000 astronomical units. 100,000 astronomical units is approximately 1.6 light years. The nearest star, Proxima Centauri, is about 4.24 light years away. This means the Oort Cloud extends nearly halfway to the nearest star. It fills an almost incomprehensible volume of space. If you drew a sphere with a radius of 100,000 astronomical units centered on the Sun, the volume of that sphere would be so vast that the entire region containing the planets, from Mercury out to Neptune, would be an invisibly tiny speck at the center. The planetary region occupies a sphere about 60 astronomical units across. The Oort Cloud occupies a sphere roughly 200,000 astronomical units across. The Oort Cloud sphere is more than 3,000 times wider than the planetary region. In terms of volume, the Oort Cloud is roughly 30 billion times larger than the volume enclosed by Neptune's orbit. The solar system, defined by the Oort Cloud's outer boundary, is not the compact structure you see in diagrams. It's a vast sphere nearly 2 light years across, and the planets, the part of the solar system everyone thinks about, the part shown in every textbook, occupies only the innermost billionth of that volume. Everything you think of as the solar system, the Sun and its 8 planets, is just the tiny bright nucleus at the center of something enormously, absurdly, overwhelmingly larger. The Oort Cloud is estimated to contain somewhere between several hundred billion and perhaps 2 trillion icy objects larger than about half a mile across. That sounds like a lot, and it is a lot of individual objects. But the volume they occupy is so unfathomably large that they're spread impossibly thin. The average distance between Oort Cloud objects is estimated to be on the order of tens of millions of miles. Each icy body sits alone in the darkness, separated from its nearest neighbor by a gulf of empty space wider than the distance from Earth to Mars. These objects are tiny, most of them probably just a few miles across, made of water ice, frozen methane, frozen ammonia, and rock. They orbit the Sun so slowly at these immense distances that a single orbit can take millions of years. An Oort Cloud object at 50,000 astronomical units might take roughly 11 million years to complete one trip around the Sun. During the time it takes that object to complete a single orbit, entire species could evolve and go extinct on Earth. Civilizations could rise and fall. The face of our planet could change beyond recognition. The Oort Cloud is so far from the Sun that the Sun's gravity barely holds onto it. Out at 100,000 astronomical units, the gravitational pull of the Sun is so weak that the gravitational influence of nearby stars becomes comparable. This is why the Oort Cloud is the source of long-period comets. A passing star doesn't need to come particularly close to the solar system to disturb Oort Cloud objects. It just needs to pass within a few light years, and its gravity can gently nudge icy bodies enough to change their orbits. sending some spiraling inward toward a sun, while flinging others out of the solar system entirely into interstellar space. The Milky Way's own structure also affects the Oort Cloud. As the solar system orbits the galactic center, it bobs up and down through the galactic plane. The gravitational tidal forces from the galaxy's mass distribution create a gentle but persistent influence on Oort Cloud objects, slowly shuffling their orbits over millions of years. The Oort Cloud is not a static structure. It's being constantly stirred and reshaped by these external forces. Here is what makes the Oort Cloud so important for our question about what the solar system looks like from the outside. The Oort Cloud is spherical, not flat, not disc-shaped, spherical. This is fundamentally different from the inner solar system. The planets orbit in a relatively flat disk. The Kuiper Belt, while puffier, is still roughly concentrated around the ecliptic plane. But the Oort Cloud is a sphere surrounding the Sun in all directions. Comets fall inward from it at random angles, confirming its spherical shape. This means that the true outer boundary of the solar system is not a disk at all. It's a shell. A vast, diffuse, invisible shell of icy objects enclosing the sun from every direction. If you could somehow light up every object in the solar system at once, make every asteroid and comet and planet and Kuiper Belt, object and Oort Cloud body glow brightly enough to see, the picture you'd get would not look like a flat disk. In the innermost region, yes, you'd see a thin flat disk where the planets orbit. A little farther out, you'd see the slightly thicker torus of the Kuiper Belt and scattered disk. But surrounding all of that, dwarfing it completely, you'd see an enormous spherical haze of points extending out to nearly 2 light years in every direction. The disk structure of the planetary region would be a tiny flat feature at the center of a vast spherical cloud. This is the solar system's true shape. It's not a disk. It's a sphere with a disk in the middle. Or more precisely, it's a series of nested structures. A flat disk of planets at the center, surrounded by a thick torus of Kuiper Belt objects, surrounded by a diffuse scattered disk, all of it wrapped inside an enormous spherical shell of Oort Cloud bodies. As you move outward from the sun, the structure transitions from flat and organized to spherical and chaotic. The neat, orderly geometry of the inner solar system dissolves into the random, isotropic distribution of the Oort Cloud. But here's the thing that might be the most haunting realization of all. Even though the Oort Cloud is by far the largest structure in the solar system, even though it defines the system's true outer boundary, even though it contains trillions of objects, it would be completely invisible from the outside, utterly and totally invisible. The individual Oort Cloud objects are too small, too dark, and too far from the sun to reflect any detectable amount of light. At 50,000 astronomical units from the sun, sunlight is roughly 2.5 billion times weaker than it is at Earth. Any sunlight that reaches an Oort Cloud object and bounces off its surface is unimaginably faint. Even with the most powerful telescopes conceivable, detecting individual Oort Cloud objects from outside the solar system would be impossible with any technology we can currently envision. And because the objects are so widely spaced, there's no collective glow. There's no diffuse haze of reflected light. There's no faint shell that you could detect as a structure. Each object is alone in the dark, too small and too dim to contribute to any visible signal. The Oort Cloud exists. It's real. It's enormous. But it has absolutely no visual presence. It casts no shadow. It creates no glow. It has no outline. This means that the largest part of the solar system, the part that defines its true size and shape, is completely hidden. An observer looking at the solar system from a distance of, say, 5 light years would see a star. Just a star. They would have no way of knowing that this star is surrounded by a sphere of icy bodies extending nearly 2 light years across. They would have no way of knowing about the Kuiper Belt, the scattered disk, or the Oort Cloud. All of those structures would be perfectly invisible. The planets, as we've already discussed, would also be invisible. The asteroid belt would be invisible. The dust would be invisible. The only thing visible would be the sun itself, shining steadily as a point of light, giving no indication of the vast, complex, multi-layered system of objects orbiting it. Let me try to capture the full scale of what we're describing here. If the solar system's planetary region, from the Sun to Neptune, were the size of a quarter, a small coin about 1 inch across, then the Oort Cloud would be a sphere roughly the size of a football stadium surrounding that coin. The coin represents the entirety of what textbook diagrams show you. The stadium represents what they don't, and the stadium is empty. Almost perfectly empty. A few trillion tiny specks scattered throughout its vast interior, each one separated from its neighbours by enormous distances, none of them visible to any eye. This comparison might be the most important one in this entire story, because it shows you just how dramatically the textbook diagram fails to represent reality. The diagram shows you the coin. It shows you Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, arranged neatly around the sun. And it stops. It tells you this is the solar system. But the real solar system is the stadium. The coin is just the bright center. The tiny, compact, visible core of something that extends vastly, incomprehensibly, farther in every direction. There is a deep lesson here about the nature of the solar system and about empty space itself. The solar system is not defined by its objects. It's defined by the space between them. The planets are footnotes. The Kuiper Belt is a whisper. The Oort Cloud is a vast, silent, invisible volume of nearly perfect emptiness that happens to contain a few trillion small, dark, frozen objects scattered so thinly that they might as well not be there at all. The solar system is space. Cold, dark, empty space, with a star at the center and a few specks of matter distributed through it at intervals so large that the matter is essentially irrelevant to the system's overall appearance. And yet, we call it a system. We draw borders around it. We give it a name. We study its structure and its history and its dynamics. We've sent spacecraft to explore tiny fractions of it. And we've discovered that even in all that emptiness, there are worlds of extraordinary complexity. Worlds with volcanoes and oceans and atmospheres and storms. Moons with subsurface seas that might harbour life. Icy bodies with organic molecules on their surfaces. Comets that carry the chemical building blocks of biology. The solar system is almost entirely empty, but the tiny fraction that isn't empty is astonishing. This is the paradox of our cosmic home. It is vast, and it is empty, and it is invisible from the outside. But within it, hidden in the emptiness, there is complexity and beauty, and, on at least one small rocky world, life. All of it invisible to anyone who isn't close enough to look carefully. All of it hidden behind the tyranny of scale that makes the solar system look like nothing more than a star. But we're not done, because there is one more structure to discuss. One more layer to the solar system that exists on a scale between the Oort Cloud and the visible sun. A structure that isn't made of rock or ice, but of charged particles and magnetic fields. A structure that is, in some ways, the closest thing the solar system has to a visible boundary when seen from outside. It's called the Heliosphere, and it might be the most important feature of the solar system that you've never thought about. Because while the planets are invisible, and the Kuiper Belt is invisible, and the Oort Cloud is invisible, the Heliosphere might be something that an outside observer with the right instruments could actually detect. And its shape, a shape we've only recently begun to understand, tells us something profound about how our solar system interacts with the galaxy around it. Every second of every day, the sun is doing something that most people never think about. It's exhaling. Not air, of course, but a constant stream of charged particles, mostly protons and electrons, flung outward from the sun's corona at speeds ranging from about 250 miles per second to over 500 miles per second. This stream is called the solar wind, and it never stops. It flows outward in all directions, filling the space around the sun with a thin but relentless flood of electrically charged matter. The solar wind carries with it the sun's magnetic field, stretching it outward like invisible threads woven through the entire solar system. You can't see the solar wind. You can't feel it standing on Earth's surface because our planet's magnetic field and atmosphere shield us from it. But it's there. It's always been there, for as long as the sun has been shining. And it does something remarkable. It carves out a bubble, a vast invisible bubble in the thin gas that fills the space between the stars. This bubble is called the Heliosphere, and it is, in a very real sense, the solar system's true outer boundary. Not the orbit of Neptune, not the Kuiper Belt, not even the Oort Cloud, which is gravitationally bound to the sun but sits largely outside this bubble. The heliosphere is the region where the sun's influence dominates, where the solar wind pushes back the interstellar medium and creates a protected cavity around our star. To understand the heliosphere, you first need to understand what it's pushing against. The space between stars is not perfectly empty. It contains an extremely thin gas called the interstellar medium, made mostly of hydrogen and helium atoms, along with traces of heavier elements and tiny grains of dust. The density of this gas is incredibly low, roughly 1 atom per cubic centimeter in our region of the Hay galaxy. That's a better vacuum than anything we can create in laboratories on Earth. But it's not nothing. It's there. And when the solar wind slams into it at hundreds of miles per second, something has to give. What happens is that the solar wind plows outward from the sun, pushing the interstellar gas away, clearing a space. But as the solar wind travels farther and farther from the sun, it spreads out and loses pressure. Eventually, at some distance from the sun, the outward pressure of the solar wind exactly balances the inward pressure of the interstellar medium. At that point, the solar wind can't push any farther. It slows down, piles up, and the boundary between the solar wind and the interstellar gas is established. This boundary has a name. It's called the heliopause. The heliopause is the surface where the solar wind's outward push is matched by the interstellar medium's resistance. Inside the heliopause, you're in the heliosphere, the sun's domain. Outside the heliopause, you're in interstellar space, the realm between the stars. The heliopause is the true edge of the sun's atmospheric influence. It's where the sun's breath finally runs out. Before reaching the heliopause, there's another boundary called the termination shock. This is the point where the solar wind abruptly slows from supersonic to subsonic speeds as it begins to feel the resistance of the interstellar medium. Think of it like a river of fast-moving water suddenly hitting a lake. The water doesn't stop instantly. It slows down, becomes turbulent, and piles up. The termination shock is where that deceleration happens. Between the termination shock and the heliopause is a region called the heliosheath, a turbulent zone where the slowed solar wind gets compressed, heated, and deflected as it tries to find a way around the incoming interstellar gas. We know these boundaries are real because we've crossed them. Voyager 1, launched in 1977, crossed the termination shock in 2004 at a distance of about 94 astronomical units from the Sun. Voyager 2 crossed it in 2007 at about 84 astronomical units. The fact that the two spacecraft crossed the termination shock at different distances tells us something important. The heliosphere is not a perfect sphere. Its boundaries are not at a fixed distance from the Sun. The shape fluctuates and varies depending on direction, solar activity, and the properties of the local interstellar medium. Voyager 1 then crossed the heliopause in 2012 at about 122 astronomical units from the Sun. This was a historic moment, arguably one of the greatest achievements in the history of space exploration. For the first time, a human-made object had left the heliosphere and entered interstellar space. The data Voyager 1 sent back confirmed the crossing. The density of charged particles from the Sun dropped dramatically. The density of particles from the interstellar medium increased. The magnetic field changed direction. Voyager 1 was no longer bathed in the Sun's wind. It was now immersed in the thin, cold gas between the stars. Voyager 2 crossed the heliopause in 2018 at about 119 astronomical units, confirming Voyager 1's findings and providing measurements from a different location on the heliosphere's boundary. Together, the two Voyagers gave us our first direct measurements of the heliosphere's edge from two different points, allowing scientists to begin piecing together the three-dimensional shape of this enormous structure. And that shape is not what you might expect. The heliosphere is not a sphere. It's not a neat, round bubble centered on the Sun with equal dimensions in all directions. Its shape is distorted, and the reason for that distortion is motion. The Sun is not stationary. It's moving through the interstellar medium at a speed of about 15 miles per second, roughly 54,000 miles per hour. This is the Sun's motion relative to the local cloud of interstellar gas through which our solar system is currently traveling, a region called the local interstellar cloud. As the Sun plows through this gas, the heliosphere gets compressed on the side facing the direction of motion and stretched out on the trailing side. It's the same principle that shapes a raindrop falling through air. The front gets flattened by resistance, while the back gets drawn out into a tail. For decades, the leading model of the heliosphere's shape was a comet-like structure. A blunt nose at the front where the Sun's motion compresses the heliosphere against the interstellar wind, and a long tail streaming behind, extending perhaps hundreds or even thousands of astronomical units downstream. This model made intuitive sense. If the Sun is moving through gas and blowing its own wind outward simultaneously, the front should be compressed and the back should be elongated, just like the wake behind a boat. But in recent years, the picture has become more complicated and more interesting. In 2015, research using data from NASA's Interstellar Boundary Explorer spacecraft, known as IBEX, suggested that the heliosphere might not have a long trailing tail at all. Instead, some models propose that the heliosphere could be shaped more like a deflated croissant or a curved, crescent-like structure with two large lobes extending on either side but no extended tail. Other models, incorporating data from the Cassini spacecraft's measurements of energetic neutral atoms, suggested a shape that's more rounded and compact than the traditional comet model, with the heliosphere being thinner and more bubble-like than previously thought. The truth is that we're still not entirely sure what the heliosphere looks like. We've only crossed its boundary at 2 points, both in roughly the same general direction as seen from the Sun. That's like touching an elephant at 2 spots on its leg and trying to guess the shape of the entire animal. The heliosphere is enormous, and our measurements are limited. Different models fit the available data in different ways, and the debate among heliophysicists is ongoing. What we do know is that the heliosphere is not symmetric. The front, the side facing the direction of the Sun's motion through the interstellar medium, is closer to the Sun than the back. The nose of the heliosphere, where the solar wind first collides with the interstellar gas, is estimated to be about 100 to 120 astronomical units from the Sun. The tail, whatever its exact shape, extends farther, perhaps several hundred astronomical units or more. This asymmetry means the heliosphere has a definite orientation. It's pointing somewhere. It's shaped by the Sun's motion through the galaxy, and that motion gives the structure a front and a back. This is fascinating because it means the heliosphere is a dynamic structure, constantly being reshaped by changing conditions. When the Sun is more active, during periods of high sunspot activity known as solar maximum, the solar wind is stronger and the heliosphere pushes farther out. During solar minimum, the wind weakens and the heliosphere contracts slightly. The interstellar medium isn't perfectly uniform either. As the Sun moves through space, it encounters regions of slightly higher or lower density gas, which can change the heliosphere's shape and size over thousands of years. Now, here is the question that brings everything back to our central topic. If you were an observer outside the solar system, looking back at it, could you see the heliosphere? Could you detect this bubble? The answer is nuanced. With unaided eyes, no. The heliosphere is invisible in visible light. It doesn't glow, it doesn't block light. It has no surface that reflects photons. You can't see it. But with the right instruments, an outside observer might be able to detect it. The heliosphere interacts with the interstellar medium in ways that produce detectable signals, particularly in certain wavelengths of light and in energetic neutral atoms. At the boundary of the heliosphere, where the solar wind collides with the interstellar medium, charged particles are heated and energized. Some of these energized particles steal electrons from neutral interstellar atoms and become energetic neutral atoms. Fast-moving hydrogen atoms that can travel in straight lines without being deflected by magnetic fields. These energetic neutral atoms stream outward from the heliosphere's boundary and could in principle be detected by a sufficiently sensitive instrument at interstellar distances. The heliosphere also produces radiation at specific wavelengths. When neutral hydrogen atoms from the interstellar medium enter the heliosphere and are eventually ionized by the solar wind or by sunlight, they produce a glow of ultraviolet light at a wavelength called Lyman alpha. This glow is faint but real. It's been measured from inside the heliosphere by spacecraft like IBEX. An outside observer with a sensitive ultraviolet telescope might be able to detect this faint emission and infer the presence and approximate size of the heliosphere. There's also the interaction between the heliosphere and the interstellar magnetic field. The interstellar medium has its own weak magnetic field, and the heliosphere distorts it as it plows through. This distortion could create subtle signatures that advanced instruments might detect. So while the heliosphere is invisible to the naked eye, it's not entirely invisible to all forms of detection. It's the closest thing the solar system has to a detectable boundary from the outside. Not its planets, not its Kuiper Belt, not its Oort Cloud, but its heliosphere. The bubble of solar wind pushing against the galaxy's thin gas. That's the feature that an advanced alien civilization with the right instruments might notice when looking at our star. This is a strange and somewhat humbling realization. The most detectable structural feature of the solar system from the outside is not any of its worlds. Not the beautiful rings of Saturn, not the storm-racked face of Jupiter, not the blue oceans of Earth. It's a bubble, an invisible, shapeless, ever-shifting bubble of charged particles held in place by the sun's exhalation and sculpted by its motion through the galaxy. That's the solar system's true silhouette. Now, let's put the entire picture together, because we've been building toward this moment for the entire journey. Let's imagine you're an observer positioned far outside the solar system, perhaps 10 light years away, equipped with godlike vision that lets you see all electromagnetic wavelengths and detect structures at every scale. What do you see when you look at the solar system? The first and most obvious thing is the Sun. It's a G-type main sequence star, yellow-white in color, middle-aged, unremarkable. It shines steadily with a luminosity that places it among the brightest stars in the local neighborhood, but nothing extraordinary. It looks like any number of similar stars scattered across the galaxy. There is nothing about its appearance that distinguishes it from countless other stars. If you look very carefully with instruments sensitive to the infrared, you might detect a faint hint of excess infrared radiation. This would come from the zodiacal dust cloud in the inner solar system, and from dust in the Kuiper Belt region, tiny grains of material that absorb sunlight and re-emit it as heat. This infrared excess would be extremely faint, but it's the kind of signal astronomers on Earth use to detect dust disks around other stars. An outside observer might notice this signal and conclude that the Sun has a debris disk, leftover material from planet formation. They'd be right, but they wouldn't be able to see the individual objects that make up that disk. They'd just see a faint thermal glow. If your instruments were sensitive enough to detect Lyman alpha ultraviolet emission, you might notice a faint glow surrounding the Sun, extending out to roughly 100 to a few hundred astronomical units. This would be the signature of the heliosphere, the region where interstellar hydrogen is interacting with the solar wind. From this signal, you could infer that the Sun has an active stellar wind pushing against the interstellar medium. You might even be able to estimate the heliosphere's size and perhaps detect its asymmetry, the way it's compressed on one side and extended on the other due to the Sun's motion through space. If you were viewing the solar system from a direction roughly perpendicular to the ecliptic plane, looking down on it from above, the dust disk would appear as a faint face-on ring. The heliosphere would appear as a roughly circular glow surrounding the star. You might infer that the system has some structure, some preferred plane where material is concentrated, and a wind-blown bubble surrounding the whole thing. If you were viewing from near the ecliptic plane, looking at the system edge on, The dust disk would appear as a thin line extending on either side of the star. The heliosphere would appear elongated, stretched in the direction of the sun's motion, and compressed on the opposing side. You'd see that the system has a definite orientation, a flat component and a round component, and that the whole thing is moving through space, creating an asymmetric wake in the interstellar gas. But what about the planets? From 10 light years away, could you detect any of them? With current real-world technology, probably not. Earth-like planets are extraordinarily difficult to detect at interstellar distances. Even Jupiter would be a severe challenge, but with sufficiently advanced instruments, using techniques like coronagraphy to block the star's light and reveal faint companions, you might be able to detect Jupiter as a faint point of light, separate slightly from the Sun. You might notice that this point moves over time, orbiting the star. From that, you could infer the existence of at least one planet. With even more advanced technology, you might detect the gravitational wobble that Jupiter induces in the Sun, a tiny back and forth motion caused by Jupiter's mass tugging on the Sun as it orbits. From this wobble, you could calculate Jupiter's mass and orbital period without ever seeing the planet directly. This is essentially what Earth-based astronomers do when detecting exoplanets around other stars using the radial velocity method. But the inner planets? Forget it. Earth, Venus, Mars, Mercury would be hopelessly beyond detection at 10 light years. They're too small, too close to the Sun, and their gravitational effects are too tiny to measure. From outside, the solar system might appear to have one large planet, maybe two if Saturn could also be detected. The rest would be invisible. The complex, diverse family of 8 planets that we know so intimately would be reduced to at most a couple of faint detections and a lot of inferred properties. This brings us to perhaps the most profound insight of this entire exploration. The solar system, seen from the outside, is not a system at all. It's a star. Everything that makes the solar system interesting to us, everything that makes it home, the planets, the moons, the rings, the comets, the asteroids, the complexity, the beauty, all of it is hidden, compressed into the unresolvable glare of a single point of light. The solar system's real appearance from the outside is, to be blunt, boring. It's a star. An ordinary star with a faint dust disk, and a detectable but unremarkable stellar wind bubble. That's it. That's what 4.5 billion years of planetary evolution, geological transformation, atmospheric development, and biological complexity looks like from the outside. A dot. And yet, this dot contains everything. Every sunrise, every ocean, every thunderstorm and every snowflake, every forest and every desert, every song ever written and every child ever born, every act of love and every act of cruelty, all of human history, all of Earth's history, all of the solar system's extraordinary diversity and beauty, packed into a point of light that an outside observer would glance at and probably ignore. There is something profoundly moving about this. The disconnect between what the solar system looks like and what it contains is perhaps the greatest gap between appearance and reality in the entire universe. From the outside, it's nothing special. From the inside, it's everything. This is true of other stars too, of course. Every star you see in the night sky might harbor its own system of planets, its own version of the complexity we find in our solar system. And from our vantage point, those stars are just dots, just points of light. We have no way of knowing, just by looking, which of those dots might host oceans and atmospheres, and maybe even life. The universe hides its treasures behind distance and the limitations of light. When astronomers search for exoplanets, they're trying to pierce this veil. They're trying to learn what's hidden around those distant points of light. Every exoplanet detection is a small victory against the tyranny of distance, a moment where we manage to learn something about a world we'll almost certainly never visit. And every detection reminds us that the universe is richer and more complex than it appears. The boring dots are not boring at all. They just look that way from far enough away. Let me close by returning to the question we started with. What does the solar system actually look like from the outside? The answer depends on what you mean by look like and from how far away you're looking. From just beyond Neptune, the solar system looks like a bright point of light, surrounded by a few scattered faint dots that you could only identify as planets if you already knew they were there. The inner planets are lost in the sun's glare. The outer planets are dim and dispersed across different parts of the sky. There is no coherent visual structure, no recognizable pattern, just emptiness with a bright center and a few barely visible companions. From a few hundred astronomical units, the solar system looks like a star. The planets have vanished entirely. The sun dominates, but it's already beginning to lose its overwhelming presence. The Kuiper Belt and scattered disk objects are completely invisible. You're surrounded by the solar wind, inside the heliosphere, but you can't see it. The only thing visible is the sun and the unchanging background of distant stars. From 1,000 astronomical units or more, the sun is just a bright star. One point of light among many. Nothing about it tells you what orbits it. Nothing marks it as special. The Oort Cloud objects around you, if there are any nearby, are too small and dark to see. The heliosphere, if you could detect it, is the only structural feature that might indicate this star has some interaction with its environment. But to the naked eye, there's nothing. Just stars. From a few light years away, the sun is an ordinary star in an ordinary part of the galaxy. A careful observer with good instruments might notice a faint infrared excess suggesting a dust disk. They might detect an ultraviolet signature from the heliosphere. They might spot the gravitational tug of Jupiter, but they would have no way of knowing about Earth, about water, about life, about the astonishing complexity hidden within the unremarkable point of light. The solar system from the outside is not the colourful, crowded, neatly organised diagram you grew up with. It's not a disk of visible planets orbiting a glowing sun. It's not a system you'd recognise or even notice. It's a star, surrounded by an invisible bubble of charged particles, embedded in a vast invisible cloud of icy debris, with a thin invisible dust disk, and a handful of undetectable small worlds hidden in the glare. Its true shape is not a flat disk, but a nested series of structures transitioning from flat to spherical, from ordered to chaotic, from compact to vast. And at every scale, the dominant feature is the same: emptiness, space, the void between objects that dwarfs the objects themselves. This is what the solar system actually looks like from the outside, and it's as far from the textbook diagram as anything could possibly be. The diagram shows you order, structure, visibility, proximity. The reality offers emptiness, invisibility, isolation, and scale beyond human comprehension. They are almost perfect opposites. But here's the thing I want you to carry with you after tonight. That emptiness, that invisibility, is not a failure of the solar system. It's a feature of the universe itself. The universe is vast and sparse and dark. Almost everything in it is separated from almost everything else by enormous gulfs of nothing. Stars are far apart. Galaxies are far apart. Planets are tiny and faint and hard to see. This is just how the cosmos works. The universe doesn't announce its treasures, it hides them. And the solar system is one of those hidden treasures. A tiny, complex, beautiful system wrapped in layers of invisibility. Invisible planets orbiting inside an invisible dust disk, surrounded by an invisible belt of icy objects, enclosed in an invisible cloud of frozen debris, all of it wrapped inside an invisible bubble of solar wind, carved into the thin gas between the stars. Layer after layer of structure, each one fascinating, each one telling us something about the history and physics of our cosmic home, and every single one of them invisible from the outside. The textbook diagram was always a kindness, a way of showing you what's there even though you'd never be able to see it. But the truth, the real truth about what the solar system looks like from outside, is more profound than any diagram can capture. It tells you that the universe is full of hidden complexity, that behind every ordinary looking star, there might be an extraordinary system of worlds, that the cosmos is richer than it appears, deeper than it seems, more intricate than our eyes can show us, and somewhere inside one particular hidden system, orbiting one particular unremarkable star, on one particular small, rocky, water-covered world that no outside observer could ever see, something extraordinary happened. Atoms assembled themselves into molecules, molecules assembled themselves into cells, cells assembled themselves into organisms, and eventually, after 4.5 billion years of chemistry and evolution, some of those organisms looked up at the night sky and started asking what it all looks like from out there. That's the real story of the solar system from the outside. Not what you see, not the star, not the bubble, not the invisible structures, but what's hidden inside all that invisibility. A pale blue dot, too small and too faint for anyone to notice, carrying the only known life in the universe, looking outward and wondering. And the next time you see one of those textbook diagrams, the neat circles, the colourful planets, the sun at the centre, remember what it's really showing you. Not what the solar system looks like, but what it contains. Because from the outside, the solar system is almost nothing. Just a star. But from the inside, from this one tiny world where you happen to live, it is everything. It's every sunrise and every sunset, every ocean and every mountain, every breath you've ever taken, every person you've ever loved. The universe hides its miracles inside ordinary looking stars, and ours is no exception. From the outside, it's invisible. From the inside, it's home. And maybe that's the most extraordinary thing of all, that something so rich, so complex, so full of wonder, can look like nothing at all from just a few light years away. The solar system doesn't need to be visible to be remarkable, it just needs to be here. And it is. And so are you. Thank you for taking this journey with me tonight. If you found this exploration meaningful, a like or subscribe helps the channel more than you might think. And the next time you look up at the stars, remember that each one of those tiny points of light could be hiding its own invisible system of worlds. You can't see them. Nobody can, not from this far away, but they might be there, richly complex, achingly beautiful, and completely hidden behind the quiet disguise of an ordinary star, just like ours. Good night.